Hello everyone, welcome back. The topic for this video is on antiderivatives, and we're going to start with a motivational example. So let's suppose that a physicist knows the velocity v of t of a moving particle and wants to know what the position of the particle is at any given time t. Now, is it possible for us to determine an explicit formula for the position function if we are given the velocity function? So in other words, what we're looking for is some function, s of t, which will satisfy the relationship where the derivative of s is equal to v. Now the answer to that question is not always straightforward, but it does lead us into the other branch of mathematics, which is called integral calculus. And so we're going to start with some of the ideas in this section. So let's first define what antiderivatives are. So a function capital F is called an antiderivative of little f on an interval I if the derivative of capital F is equal to little f for all x in I. So you can think of antiderivatives as being the opposites of a derivative. So what we're really looking at is working backwards from our function. So we're given some function, and we want to know what the original function is so that when we differentiate capital F, we get little f. So as an example, let's suppose that our function f of x is equal to 2x. So we're looking for a function, capital F, such that its derivative is equal to 2x. So what function, if we differentiate it, gives us 2x? So in other words, is there some way for us to undo the operation of differentiation? Now, if we're dealing with power functions, we do have a formula to calculate its antiderivatives. So if our function f of x is equal to x to the power of n, so we have a power function, then an antiderivative for f of x is given by the following formula. So its antiderivative is calculated by adding 1 to the exponent, and then we divide by that same exponent. So we divide by n plus 1. And this formula will hold as long as the exponent n is not equal to negative 1. If the exponent on x is negative 1, then there is a unique antiderivative for that case, and we will cover this in the next chapter. So going back to our example, if we want to find the antiderivative of 2x, we can apply this formula. So the 2 is a constant, so we will leave that there, multiplied. We're going to add 1 to the exponent, so 1 plus 1, and then we divide by that same exponent, 1 plus 1. So simplifying, this gives us 2 times x squared over 2, which can then be simplified to x squared. So the antiderivative of 2x is x squared, because if we differentiate capital F, we get little f. Now what about the functions x squared plus 1 or x squared plus pi? Now are these functions also antiderivatives of little f? Yes, they are, and in fact, if for any constant c, then the function f of x plus c, where capital F is the n antiderivative of little f, is called a general antiderivative. We know that if we differentiate any constants, then they will go to 0, and so differentiating any of these functions will give us the same uh, function little f. And so this gives us the following theorem. So if capital F is an antiderivative of little f on some interval I, then the most general antiderivative of f on I is capital F of x plus c, where c is any arbitrary constant. So let's have a look at some examples of finding the general antiderivatives of functions. So let's start with f of x equals x minus 3. So let's find our general antiderivative of this function by applying the formula for finding antiderivatives of power functions. So we have x minus 3, and you can think of the constant 3 as having the power function x to the power of 0. We know that x to the power of 0 is 1, and so we can calculate its antiderivative as follows. So capital F is equal to the antiderivative of x. We're going to add 1 to the exponent, so that is x to the power of 2, and then we divide by that same exponent, so that gives us x squared over 2, minus 3 times x. We add 1 to the exponent of 0, which is 1, and then we divide by 1. And we really don't need to write the division by 1. But then we also need to add any arbitrary constant c for its general antiderivative. So our general antiderivative is x squared over 2 minus 3x plus c. Now we can always check whether we have the correct general antiderivative if we differentiate this function. So if we differentiate capital F, then we should get little f as its derivative. So let's have a look at example B. We have f is 1/2 plus 3/4 times x squared minus 4/5 times x cubed. So now let's find its antiderivative. The antiderivative of 1/2 is 1/2 x plus the antiderivative of 3/4 times x squared. So we have 3/4. Now the antiderivative of x squared, we will add 1 to the exponent, so that's x cubed, and then we divide by that same exponent, which is 3. Then we subtract 4/5 times the antiderivative of x cubed. So we add 1 to the exponent, which gives us x to the power of 4, and then we divide by that same exponent of 4. And lastly, we add any arbitrary constant c. So we can simplify this to 1/2 x plus 1/4 x to the power of 3 minus 1/5 times x to the power of 4 plus c. Now in the third example, we have f is 7 times x to the power of 2/5 plus 8 times x to the power of negative 4/5. So again, let's find its antiderivative. So we have 7 times x to the power of 2/5 plus 1, which gives us 7/5, and then we will divide by that same power, which is 7/5, and then we add it to 8 times x to the power of negative 4/5 plus 1, which is 1/5. Then we divide by 1/5, and then we add a constant c. So let's simplify our fractions. So instead of working with multiple fractions, let's multiply by the reciprocal of the denominator. So we have 7 times 5 over 7 times x to the power of 7/5 plus 8 times the reciprocal of 1/5, which is 5 over 1, times x to the power of 1/5 plus c. And we can simplify this to 5 times x to the power of 7/5 plus 40 times x to the power of 1/5 plus a constant. For letter D, we have x to the power of 5 plus 2x minus x to the negative 3, all divided by x to the power of 4. So let's first simplify our functions. So we can split the fraction into 3 separate fractions. We have x to the 5th over x to the 4th plus 2x divided by x to the 4th minus x to the negative 3 divided by x to the 4. And using the law of exponents, we can simplify the powers of x by subtracting the exponents. So we have x plus 2 times x to the negative 3 minus x to the power of negative 7. And now we can calculate its antiderivative. So to find the antiderivative of x, we add 1 to the exponent, so that's x squared, and then we divide by that same exponent, which is 2. We then add it to 2 times the antiderivative of x to the negative 3. Adding 1 to negative 3 gives us negative 2, and we divide by negative 2. And then we subtract x. We add 1 to the exponent, which is negative 6, and we divide by negative 6. And we add a constant c. So now we can simplify. We have x squared over 2 minus x to the negative 2 plus x to the negative 6 over 6 plus a constant. So now let's have a look at some examples from physics. So here we're given some information about a moving particle. So let's have a look at 2a. We have the velocity function, which is given by 2t minus 1. And we're also given some initial data. We're given that the position of the particle at time 0 is equal to 1. And so what we want to find is the position function s of t of the particle. So to find the position function, if we're given the velocity function, what we're looking for is the antiderivative of the velocity function. So the position function will be the antiderivative of v. So if we find the antiderivative of v, that will give us our position. So the antiderivative of 2t is 2 times t squared over 2 minus 2t plus a constant. And this can be simplified to t squared minus 2t plus a constant. And now we can use the initial data to determine the constant c. We're given that the position of the particle when time is 0 is equal to 1. So s of 0, which is 0 squared minus 2t plus c, this must be equal to 1. And that should be 2 times 0. And so now we have an equation which involves the constant c. We can then solve for this constant. So here we have 0 minus 0 plus c must be equal to 1. And so this tells us that the constant c is 1. And so the position of the particle is given by t squared minus 2t plus 1. So now let's have a look at the example C, and then we'll leave the examples B and D in the lab. So in example C, we're given that the acceleration function is given by 2t plus 1 and some initial data, the position of the particle when time is 0 is equal to 3, and the velocity of the particle at time 0 is negative 2. So if we want to find the position function s of t, and we're given the acceleration function, then we need to find the antiderivatives of this function twice. So one antiderivative will give us the velocity function v, and another antiderivative will give us the position function. So the velocity function will be the antiderivative of the acceleration. So if we calculate the antiderivative of 2t plus 1, then that will give us velocity. So its antiderivative is 2 times t squared over 2 plus t plus a constant c, which can be simplified to t squared plus t plus c. Now we can use the initial data to determine the constant c. We are given that the velocity at time 0 must be equal to negative 2. So 0 squared plus 0 plus c must be negative 2. And solving for c, we end up with c being negative 2. And so the velocity function is given by t squared plus t minus 2. So now we can determine the position function by taking another antiderivative. So the antiderivative of t squared is t cubed over 3. The antiderivative of t is t squared over 2. And the antiderivative of negative 2 is negative 2t. And we add another constant. And just to not get confused with different constants, we'll call this one d. And now we can use the initial data for position to determine the constant d. We're given that the position of the particle at 0 must be equal to 3. So 0 cubed over 3 plus 0 squared over 2 minus 2 times 0 plus d must be equal to 3. And this will allow us to solve for d. which is equal to 3. And so the position of the particle is given by t cubed over 3 plus t squared over 2 minus 2t plus 3.